Hello everyone, my name is Beruz. This is the first session for the AF workshop, which is about the practical arc flash protection, and this session is about the fundamentals of power systems. So the topics for this session are basically the distinction between utility and industrial distribution, voltage classification, multiple voltage levels in power distribution, types of distribution arrangements and redundancy, and types of fault. In other words, what I'm going to do in this session is to tell you about the preferences in terms of the voltage selection between the utility and industrial applications, and under what circumstances and on what conditions we just classify the voltages at transmission, distribution, subtransmission, HV, LV levels, and what are the considerations in between. And after that, we would be able actually to move on to power system protection and faults, and just make a relation between what we learned for these distribution systems, transmission systems, and power system protection. So at the very beginning, let's talk about the main types of distribution system that we have got. So distribution of loads can happen at a utility level or at an industrial level. Let's say that distribution can be done in a for example, zone substation that belongs to a power company, or it can happen inside an industrial site, like the switchgear that you may find in a factory, for example, or a workshop or something like that, okay? So we have got different criteria actually in terms of the configuration for the distribution system that we consider, that we select, that we choose. From the perspective of the utility, what matters is that this distribution of loads must be done very flexibly and quickly. In other words, the single line diagram, the configuration of the bus bars and loads should be selected in a way so that transferring of loads between the feeders are easy, transferring of supplies are easy, and at the same time it has to be cost effective. It mustn't be so expensive. What happens to the industrial distribution? First thing is that they would like to have the continuity of supply. Okay, under no circumstance they would like to have an outage in their system, because that's, for example, the production line. It's a shop, it's a hotel, okay? It's a factory. So basically the first thing is that they would like to have a reliable source, and after that they would like to have the ease of control so that they can have full control over each load. They can prioritize the loads or something. Therefore, we need to have some standards in between so that we understand to what kind of load, what voltages should be applied to. So first thing, British standard BS and IEEE, which is the European standard, basically, they are determining this definition. So they say, if you're talking about AC, the margin is 1 kilovolt. If you're talking about DC, the margin is 1.5 kilovolts. So anything below 1 kilovolt, this is what we call the LV system, okay, or for AC. Or anything between 1500 volts for DC, this is what we call the LV system. Other than that, this is what we call the HV system. So this is the definition as per the British and European standards. However, things are a little bit different when it comes to the American standard IEEE 141 as of 1993. In that case, rather than having 2 voltage levels, they have defined 3 voltage levels of LV and MV and HV. So again, the margin of 1 kilovolt is valid. So they say that this is the nominal voltage up to 1 kilovolt is what we call the LV. So what are the most important famous ones? 380 volt system, 415, 480 volts. So this is what we call the LV. All right. And what is the margin for HV? The margin for HV is 100 kV and above. Okay, so like what? Like 115 kV, like 132, like 138, 230 or something. So these are what we call the HV. What is between the two is what we call the medium voltage. Therefore, it must be between 1 kV and 100 kV. Like what? Like the examples that you can find in here, like 6.9 kV, like 12 kV, 11 kV, 13.8 kV, all right, 69 kV. So these are examples of medium voltage that are widely used in industry especially, right? So when it goes into the discussion of selection of voltage, the first thing that happens is that we need to split the power system into different parts. So we have to differentiate between different parts of the power system. So what are the main components? What are the main segments and sections? So we have got from the very start of it, we have got generation, and then we deliver that to the transmission system, and then sub-transmission system, then it will be stepped down to distribution, and then it goes to the utilization. So generators are normally at in the range of, for example, 12 kV or something like that, 22 kV, 20 kV or something, okay? So basically, according to what we learned in here, okay, they are within the medium voltage range, okay? So this is what we understand. Transmission system, normally we are, let's say, transferring the load or supply at 132 kV or 230 kV or something, so even higher. So transmission basically is within the range of HV. And then at times we may have a sub-transmission system so that this HV again is transferred into basically MV, something like 132 to 33 kV system, okay? And then again, this 33 or 22 or whatever will be converted into LV, something like 480 volts or 400 volts or 380 volts or something, right? And this is what we call the LV. That LV can be used either in a distribution system or for utilization, for example, giving it directly to the homes or something. So these are the selection of voltages. Therefore, when it goes into the distribution and utilization voltages, as it says in here, domestic, commercial, and small industry loads at LV, huh? You have got shops, you have got houses, you have got, I don't know, small businesses, okay, small businesses. You are using normally LV. When it goes to a little bit bigger businesses like cinemas, for example, shopping centers or something, so the first thing is that the power has to be delivered at medium voltage, and then it will be reduced down to LV, right? So it means that these kind of businesses normally they have got their own distribution transformers. When it goes again into large industries, they have got a mix of MV and LV and loads and transformers and drives and something. And therefore, distribution and utilization can involve more than one voltage, right? Because you need to have the to convert all these voltages together, especially as the business becomes larger and larger. Therefore, we need to have a number of options for the voltages, so distribution voltage options, depending on what location you are talking about. If you are talking about receiving and distributing ends, or you are talking about the supply end where. Okay. Sometimes, okay, so you may decide to have the same voltage for the receiving and the distribution ends, okay? So why is that? You would like to avoid the transformer, right? You would like to make it cheaper. Good. But at the same time, remember, if you need to have some kind of regulation on the voltage like what you have got on the tap changer, right? You cannot, because there is no transformer. And at the same time, if you would like to apply a particular earthing system, which is normally applied to the neutral, let's say, point of the transformer, again, you would not be able to do that because there is no transformer. So no independent earthing for the plant would be possible. All right. Therefore, it is not normally good. It is not good to have the receiving and distributing ends at the same voltage. So it requires us basically that at the receiving end we have got higher voltages. So we need to have two different sorts of voltages, and therefore we need to have a transformer. If we have got transformer, we can apply the on-load tap changer, for example. We can have good control over the voltage profile and voltage regulation. That transformer also can act as a buffer, for example. So what's the point? The point is that that transformer, if well designed, can mitigate, stop harmonics, voltage dips or something like that from the system, okay? And also it can provide you with a good system earthing, that transformer, okay? So this is just an example of a typical utility system. As you can see, we have got a number of buses, transformers, different voltage levels. So some of the bus bars are at the same voltage, but many of them are not at the same voltage. So for any of them, you can see that we have got a distribution transformer. So the supply is coming from different points and not from one point. So now let's focus on the distribution side of that. For distributing the load to the load centers and to the commercial loads and business loads and residential loads, okay, we have got a number of options. One of them is what we call the radial distribution. It means that you have got just a single incoming feeder. Okay, a single incoming feeder you have got. So between the source and the basically the let's say the load, there is just a single incoming feeder. So if this is your bus bar, okay, this is your load, this is your feeder basically, and this is the load in here, and you have got just a single feeder, and this is the circuit breaker at the very beginning of the bus bar, okay? So this is radial distribution, as we understand, right? So what's the good thing about that? Well, the good thing about this thing is that it is the cheapest of all. All right, it is the cheapest of all. However, what is the bad thing about that is that, well, if there is a failure, if there is a fault or something like that on this line, okay, what happens is that you will have a total outage of the radial feeder and there will be no backup. Okay, so it says in here that restoration only after the problem is rectified. So basically, there is no redundant, no nothing. Okay, so under what situation you may prescribe such a distribution if the load is not basically very important and you're not going to spend a lot of money or something, protection and line cables or something like that. Okay, so this is what happens. So not desirable, as it says in here, but critical production processes are involved. You have got mining, you have got oil and gas or something like that. Okay, so how can I, for example, improve this? Easy. If I've got enough money, what I would do is that rather than providing one supply, one feeder to the load center, I will do two. So rather than having one supply, I will make it two. But the problem is, this is what we call the parallel feeders. Okay, this is very good. So this time you have got redundancy basically, but what happens is that you need to have in terms of the protection, you need to have the directional protection applied in there. Other than that, there will be confusion in here. You would not be able to understand if there's a fault in here. The supply would come from this end, and also the supply would be able to come from this end. So definitely you need to apply, let's say, the directional protection in here. Another option is that you can make it a ring, you can make it a loop, as it says in here. So you would like to have full reliability, okay? So we can consider something like that, like a loop, like a circle, and connected to that you have got a number of, for example, different bus bars connected in between, like this and this and this and this. And for example, this is the supply point, and basically you have got a number of distribution transformers connected to each of these, and you have got their own circuit breakers and whatever. Okay, this is good because if you, for example, you've got a circuit breaker here and you've got a circuit breaker here, if there is a fault in here, okay, again, so there from here there will be I faults. Okay, I faults will go this way, okay, which is not good basically, but this load in here still can be supplied from this end. Okay, so this is what we call the full reliability. Supply can be restored to all the transformers without waiting for repair of faulty section. But again, as I said before, for parallel feeders in here, the problem, this is not the problem, but you have to pay more actually, is that you have to consider the directional protection in here. So again, another good thing about this ring, as it says in here, is that easy to extend the ring, okay? So you can easily add some more, for example, bus bars on and on and on in here with no difficulty, all right? So not a problem, you can extend the ring, okay? But as I said, the protection and control and cons side of that could be a little bit difficult. Spare lines, so you have got a line, for example, this time, a line, and you can get a number of spare lines out of that. So again, this is another way of distributing, let's say, the load to the, let's say, the customers, and this is good as long as you can coordinate the protection in here, that will be very good. And again, new extensions are possible, so again you can add and add and add as long as the rating of the line allows, of course. But again, as it says in here, that the lack of redundant feed for load connected to a spare lines. Again, per load, you have got only one feeder, okay? So there is no redundancy or something, okay? So again, we do such a thing for not very important loads, okay? So if someone asks you about the components of the distribution system, you would say, well, in very general terms, you have got a bus bar, for example, you have got an incomer, very, very simple, right? And then you have got a transformer, or for example, two transformers in here. This is what we call the H-type configuration. And then this is the LV side of the transformers, and you have got a number of loads connected in here. So basically what happens is that you have got a switchboard in here at the secondary side of the transformers, and you have got another switch here at the HV side of the transformers in here. So this is the distribution system component at the from this end, from this end down. This is your distribution transformer, distribution system. So basically you need to have an incoming section, which can be a direct line, or it can be, as I've shown in here, the transformers or something. Also in terms of, for example, having a full redundancy, at times you may decide to have an in-plant generation emergency, so that if you lose contact to the incoming supply, basically you can turn on your generator and feed the loads in here for critical loads, as it says in here. So you may decide actually to provide the supply to a number of critical loads that you have got in here, all right? So you have got a step-down transformer, for example, if this is your load, you may have a transformer here, or you may have a transformer here, okay? So you have got a step-down transformers, and basically the low voltage distribution system and control gear for individual loads. So this is what happens for the components of that. Now, even if I said that, I can rearrange all these things in many different forms. This is very simple thing. Main distribution at the receiving end, all right? So this is exactly what I told you right now. So you have got a switchboard in here, and inside that you have got a number of circuit breakers. So this is your switchboard, and for example, some of these loads, as you can see in here, may be connected to distribution transformers, so they just convert that distribution voltage of 11 kV or whatever it is into something like 415 volts, right? So this is a very, very easy plan. However, we can also have it like main distribution after stepping down. So rather than connect it directly to a main incoming feeder of 11 kV, you may decide actually to put a transformer here. For example, your switchboard is 11 kV, okay? Your switchboard is 11 kV. However, the main supply is 33 kV. You cannot connect a 33 kV supply to an 11 kV switchboard. Therefore, you need to have a transformer in between, which is 33 to 11 kV, and again, the same thing, okay? So the rest of that would be the same thing, right? Large motors, okay, so sometimes you have got large motors. These large motors may work with 11 kV, with 6.6 kV, with 3.3 kV or something like that. So if your switchboard already is an 11 kV one, you may decide actually to connect these motors directly to that 11 kV bus bar. Okay, so the rest of that again is the same, right? So these motors, so what happens is that, and as you can see in here, we have got a standby generator in here. So the problem is the start up of the motors, for which you need to have very, very careful. Other than that, there you might have some basically voltage drop on this 11 kV bus, and as a result of that, the circuit breakers may be tripped, and you would lose the let's say the supply to your load center in here. So in starting up these motors, you have to be very, very careful, right? Or the motors may not be, for example, 11 kV. They might be 3.3 kV, right? Like what you have got in here. So again, before you connect them directly to the 11 kV bus bar, you need to have another transformer, let's say 11 to 3.3 kV, so that they can connect them to your distribution systems, okay? Same thing applies, for example, rather than motor, you may have a number of residential loads, like, for example, or small motors, like 415 volts motors that you connect to MCC, motor control center, or, for example, you may have a lighting system, 215 or something. So you can see that for LV distribution, it can be three-phase, like what you have got in here, 415, or it can be single-phase, like 240 volts in here. So as I said before, you may have different voltages. As you can see in here, it says three-phase and single-phase LV power loads. So you have got a combination of all of them at the LV side, all right? So when you think about, again, industrial distribution, they would like to have duplicate of everything, duplicate of the supply, duplicate of the transformers, duplication of the loads or something, and for which they need to have bus coupler circuit breakers so that they can isolate the system. What's the benefit of that? The benefit is redundancy. And all the time they need to make sure that there is no outage to the supply. There is no outage to the transformer base. There is no outage to the loads. Even at times they may decide to have two bus bars rather than one bus bar. So they may have some double bus bar or main and transfer or main and reserve bus bar configuration. So the idea is to have 100% reliability and redundancy if they can in their system. So they have got many different ways to do that, okay? So redundancy in primary system, okay? So we would like to have, rather than single supply, we would like to have duplicate supply. Is it possible? Oh, yes, you can. So rather than having one, for example, supply to the load, you may decide actually to have two supplies to the load, and they are fed from the same transformer. Okay, so this is what we call the selective redundancy. So two feeders are connected to each load, basically one feeder used at a time and can be selected. So it's not like both of them are in service. You can see that we have got switches, okay? Yes, you have to spend a lot more money. You have duplicated the feeder, but you will have the benefit of that. So what's the benefit? The benefit is reduces time of interruption, automatic restoration schemes. So as soon as there is a, for example, fault on this one, you will bring this one into service and with not a problem, okay? So you have got full redundancy in here, or at times you may decide actually to make it a loop or ring. So rather than having two feeders to the load, you have got only one, and you have got only one, and you have got only one. However, you will connect these ones together to make a loop. Again, that's fine as long as you have got the money, that's fine, and as long as you are ready to apply the directional protection schemes in there. So sometimes that redundancy is applied to the outgoing feeders. So again, this is your switchboard, okay? This is your switchboard, and this is just one single load. But rather than having one outgoing feeder to it, you have got two outgoing feeders, and again you have got a switch in here. So you may decide actually to feed this load from number one, and if required, if there's a fault, for example, on number one, you just take it out and just bring number two in service. That's your decision. Again, you have got redundancy on the outgoing feeder in here. It can be applied to the incoming supply, basically, right? What you have got in here. So again, this is the same transformer bay, but it is supplied from two lines, and you can see that we have got a changeover switch in here. And basically, again, that's your decision. You may decide actually to be connected to number one by default, and if there is a problem with number one, by means of that changeover switch that you can see in here, you can easily switch to number two, right? So this is another way of doing that. Same thing can apply to transformers. So one incoming and one outgoing per load with the bus coupler circuit breaker in between. However, this time you are duplicating the transformers. So rather than having one transformer connected to your LV switchboard, you have got two transformers in here. Or you can have a combination of both. So as you can see in here, you can have two transformers, and at the same time you can have two incoming lines actually connected. This is the best of the best. For example, transformer number 1 can be supplied from this, or transformer number 1 can be supplied from this, or transformer number 2 can be supplied from incomer 1 or incoming 2, or both, or whatever, right? So you have got a lot of options actually to apply in here, but of course it is more expensive, right? You can have even redundancy for the LV systems. So rather than, for example, having one supply, as I said, you have got two supplies and you are connecting them to a switchboard, but rather than having one switchboard, you have got two, 1 and 2, and in between there is a switch which is normally open. You have got a circuit breaker or isolator switch in here, which is normally open. So first of all, you have to split them, and then basically after that, you can connect them all together. Or again, something like that loop that you have similar to that, this time you can have for LV system. So rather than duplicating the feeder, you can connect them at the secondary tie bus area together to make a to connect them to a spare transformer, something like that. Okay, so this is one transformer main, this is main, this is main, but you have got a sparing transformer, and also you have got future transformer here. So the good thing about that is the extension. You can easily extend other things in here. So that was regarding the planning side of that. And now let's move on to protection. So you know what is the meaning of fault? The fault is abnormal situation, like short circuit, like phase-to-phase, earth fault, single phase, I don't know, all these things are faults. There are different causes for the faults, like, for example, flashover, like the birds, for example, coming onto the transmission line distribution, like, for example, the puncture in the cable, or failure of installation, or installation degradation, as we say. Whatever is the fact, there are some effects and consequences, like what? Like overheat, like over voltage, like electrodynamic forces that can produce unwanted torque, and that unwanted torque can break the bus bars, for example. It can put a lot of pressure on the joints and break them, and worst case scenario is that you may have danger to the lives of the people. There could be arcing and fire and explosion and things like that. So these are the consequences of fault. So what types of faults we have got? You can classify the faults in many different ways. You can say they can be transient and permanent. Permanent, like, okay, so you have got a puncture in a cable, that's it. You have got a breakage in a tower line, okay, that's it. But sometimes it's transient, like there's a wind, okay, a blow of wind, okay, strong blow. So just for a moment, two phases actually touch each other, and that's all, and then everything is normal. So we have got transient and permanent faults. We have got active and passive faults. If they are strong faults, they are what we call the active or solid faults, but sometimes it takes time actually for that fault to show it itself, like overload, over voltage, power swings. They do not have an immediate consequence, but sooner or later they will show themselves to you. So from another point of view, you can say we have got single phase, phase-to-phase, three-phase faults in a power system. Again, you can say that we have got symmetrical and asymmetrical fault. Especially symmetrical is for the three-phase faults, and asymmetrical is for the single-phase faults. What's the problem? The problem with asymmetrical is that you have got an offset, DC offset in here, and it means that for the first cycles, seconds of the fault, you have got a lot bigger amplitude and magnitude that is out of your expectations, and your system may get into trouble. So this is a summary of all the types of faults that I told you. So the single phase to earth fault, as I said, it is the most common type of fault. Normally it is due to the insulation failure, and what happens is that if your system is solidly earth, that is, you have directly connected the neutral point to the ground, in that case you will have the maximum earth fault current in here. This is good and this is bad. This is good in terms of being able to detect the fault pretty much quickly. Being bad in terms of if the fault current is very strong and the protection system is not able to clear the fault in time, in that case your system will be significantly damaged. Also, we have got face-to-face fault. It can be face-to-face or it can be face-to-face to earth. Okay, so earth could be involved or not involved. This is very common in cable systems, and again you have got a current similar to that single phase to earth, but as it says in here, it is the amplitude of that is lower. Okay, and worst case, normally this is what we consider is the three-phase fault that we consider in theory that it causes the maximum fault current. But sometimes, for your information, the three-phase fault current is lower than the single phase to earth fault. And what's the reason? Because, for your information, the amplitude of fault current depends on the impedance between the source and the fault point. It depends what kind of impedances are between the two. Okay, so therefore, as I said, when you think about the fault current intensity or magnitude, it has to do with the circuit impedance from the source to the point of fault, and also the type of fault, whether it's three-phase, face-to-face, single-phase, voltage fault, arc fault, and also the type of earthing that you have got available in there. So this table gives you a comparison between different fault currents and the intensity depending on the configuration that you have got. So the main issue is, are there any necessity actually to limit the fault current? Oh yeah, depending on your system. So you have got different basically ways to do that. For example, one of the things is we have got current limiting reactors. Okay, it depends. What is the thing you are going to limit? Is that the three-phase fault? Is that the single-phase fault or something? Okay, so it depends. What is the thing you are going to do? If you are going to limit the earth fault currents, in that case, what you would do normally is that if this is your neutral, if this is a three-phase system, and if this is the neutral point, rather than directly connecting it to the ground, what you would do is that you will put a resistance in between. This is what we call the NER. Okay, so neutral earthing resistor. So by means of this resistor, what happens is that you are limiting the earth fault current that will come over here as a result of the fault in the system, right? So if this is your three-phase system like that, and if you've got a three-phase to earth fault, single-phase to earth fault, the fault current will be let's say connecting from the fault point to the intentional earthing system that you have connected in here, and this I fault will be basically limited by means of this resistor that you can put in here. Now you can put a resistor, you can put a reactance, you can put an impedance. You have got again different ways of basically limiting them. So therefore, from this end, system earthing could be many different ways. So it can be something like an unearthed system. Okay, so you've got a small system. The earth fault currents as per your calculations are not very strong. So you're not going to spend a lot of money. You would say, well, I'm not going to put any kind of earthing system in here. I'm just going to leave it unearthed. Okay, so what's the good point about that? Okay, less expensive, of course, and as long as the fault currents are very low, not a problem, and you are not going to have any outage, and therefore you have got better continuity of supply, better reliability. However, if there is a fault, in that case you're going to get into trouble, because that fault is not going to be detected because you have not provided it. I'm talking about earth fault. That earth fault will not be detected because you have not created any earthing system, right? And if it stays in the system, that can cause a problem like insulation problem in the long term, right? Also, if a second fault occurs, in that case there will be a connection between the two faults, and you do not have any protection system, and your system is blown, right? So therefore, it is much to your benefit that if you have got something like a neutral point available to you, you just make it solidly earthed, okay? So as I said, you are getting the maximum earth fault current in here, which is good as long as the fault current is low. So you have got fear that if you have got a CT in here and if you connect this CT to the earth fault relay, right, your fear is that this earth fault relay may not be able to detect the fault current. Okay, in that case, you just make a decision to make it solidly earthed. Okay, so in this case, also the good point about that is that there is no transient and a steady overvoltage, but for that unearthed system, yes, we have it. Right? So the only problem with this is that if the fault currents, as it says in here, are high, in that case, you are not allowed actually to make it solidly earthed. So what is the good point? So okay, so either you can make it reactance earth system, or you can make it resistance earth system, so that you will control the flow of earth fault current, right? And at the same time, again, similarly, you do not have any transient over voltages, and all is good. Okay, my dear friends, I hope you have enjoyed this presentation with me. Thanks very much for listening to me, and soon I will record another one for you guys.